some designs that we're kind of familiar with, the paper clip in particular. And in section 5.2 of the book, it goes through several of the design processes for designing a paperclip and also designing a machine that will build a paperclip. And there's a lot of things to consider. And first of all, you have to consider how we're going to go through this engineering process. What is the need? What is the problem, right? What led to the design of, the invention of the paperclip? Well, I think it's pretty obvious. When we started using loose leaf paper instead of rolls of parchment, we needed a way to keep them together. We needed a way to keep them in order. And they came up with all kinds of things to do this with. And even in the past few decades, there are many methods for holding paper together that are completely different. We have staples, we have grommets. The CIA forever used a stick pin through the corner of their documents. And it was a stick pin that folded back instead of a staple. I mean, just weird, all these different weird inventions to hold stacks of paper together. And the paperclip, of course, is one of them. The great thing about the paperclip, of course, is that it is not a permanent solution, but it's pretty good. It's almost like a semi-permanent solution. And it's removable, and of course, it's cheap. It's a cheap and effective thing. And so, if we're going to design a paperclip and design a process for making paperclips so that we can deliver paperclips into the marketplace, sell them, and everything else, then we're going to have to go through this process. First by identifying the need and defining the problem. Then we, of course, will assemble a team. We will identify the constraints. We'll do all these different things that you have to do in the engineering process, but we'll apply it directly to paperclips. So how do we apply them directly to paperclips? That's the real question. So what is our real need? Well, hold paper together, but is there more to it than that? Sure, there's more to it than that. I want to be able to hold 5 to 10 pieces of paper together. I want to be able to hold paper together in such a way that I can undo my holding the paper together. I want it to be cheap. I want it to be small. I want it to be easy to use. All these different things are part of that, defining this problem that we have. And then when we assemble a design team, we're going to probably need to have somebody in that team that's going to use paperclips. Well, everybody will use paperclips, so we don't really need to bring anybody from the outside. An engineer will do, but probably a mechanical engineer will do better than other types of engineers, since this is probably going to be a mechanical kind of process. But we also might need a materials engineer, because we're going to make it out of something. We might need to have somebody on this team that understands materials fairly well. We're probably going to want a manufacturing engineer or a systems engineer of some kind, so that when we design the factory for making these things, that he can be there to have input and help us to understand the best way to do that. So we assemble our team. And then we start to identify constraints and put some more details on this. How big are we going to make it? How cheap do we want it to be? How easy do we want it to use? What does easy to use mean? Does that mean I want to be able to use it with one hand, with 2 fingers? Do we want it to put itself on the paper? Maybe we want to make a self-clipping paperclip. We start to really hone it down to a very, very specific set of ideas that we're trying to accomplish. In this particular case, on page 132, they have chosen 5 criteria that they want to meet. In this case, they have reliability. They want it to be very reliable so that it works every time, right? So something that's very reliable, very important that it be reliable, they give it a ranking of 5. The compact design and the weight of this object, they give it a ranking of a 3. And then they also say the convenience is a 5. They want it to be extremely convenient to use, very easy to use, as well as reliable. And then the low cost, they give it a very low rating. I wouldn't have given it a low rating, because if you're going to use a lot of them, you want to be low cost, so I might have given at least a 2 rating for that. But they are actually setting up their project for success by defining what success is. The successful paperclip will first of all be very reliable and very convenient, because those are the highest rated properties that they came up with as they were trying to put more details into their design, into the beginning of their design development here. And then the next two things that were more important, or most important, were the compact design and the weight. So they're going to think about things that have compact designs and weight. They're going to make that kind of their second priority. Last priority is the cost of it. They want it to be a low cost, but that's not the highest priority. So all these things are going to contribute now to the different ways they're going to design the paper clips. Now let's take a look at their different designs really quick that they've given us. So here are the different designs of the paper clip that they give us. They've got 5 designs here. Hopefully it'll come up here eventually. There it is. Some autofocus going. There we go. So here are the 5 possible designs for the paper clip. And where do they get these from? Well, they just started throwing ideas out there. Brainstorming session, right? So they come up with all kinds of crazy ideas, and they put them out, and what are they going to do with these? They're going to rank them according to the criteria that they're trying to meet for a great paperclip. They want this thing to be convenient and to be reliable, right? Well, let's talk about these. Which ones of these would be not convenient or not reliable? I would say that these two right here would be the least convenient of all. Why? How do you think these that I would call these the least convenient? If you go to grab a paperclip like this made out of wire, what's going to happen to your finger every time? You're going to poke you. That's not convenient, right? You don't want something to poke you. It also makes it a little bit unreliable because, injury is not a reliable thing. So maybe I'm going to say that those two are not very reliable. Another thing is, because I'm an engineer and I understand a little bit about materials, you have a very small amount of materials in each of these compared to these other ones. And the smaller amounts of material are going to be less reliable because we're going to be stretching these things and bending them. So maybe I want to consider not having such a small amount of material in my paperclip. And maybe we even test them because they're pretty easy to make. Just by hand we can test them and see how reliable they are. However, what do these things have going for them? This one right here is going to be super easy to make. It has 1-2 bends in it and you're good to go, right? You take a wire, bend it twice, you're done. So this one has, this one is the simplest design to make, so it's probably going to be the cheapest. This one is probably the next simplest design to make, except for maybe this one. This one right here is very simple to make. You just roll up the wire, cut it, and you're good. This one also has kind of a little bit more material to it, so it might be a little bit stronger for us, a little bit more reliable. This one right here, again, a lot more material to it, but it also has a lot of bends in it, making it a little more complex. This one, however, look at this one. This one is actually a combination of the very simple in design, just 3 simple bends, has a fair amount of material, fairly easy to use. Can you use a paperclip with one hand? Absolutely. Right? And so you can start to see why this one is the most popular paperclip in the world. Because it meets all of those criteria quite easily. Right? But you first have to come up with these ideas so you can pick that one as the best one. And that's what comes in next. So after you've come up with these solutions, you start to do a feasibility study where you are going to analyze these designs, both analyzing them on paper or with computers, and also by figuring out which ones cost the most, which ones are going to be hardest to make, which ones are going to be most convenient. Essentially, you start ranking each of your designs according to your criteria. And our criteria were reliability, compact design, weight, convenience, and cost. So you rate all of them, all of these designs, how convenient are they, how reliable are they, and then you plug those into a formula that is based on these based on these weights that you gave them. So if you have a high reliability, that's really good for you because it has a weight of 5. But if you have a really good low cost option, it doesn't help you so much because that's rated a 1. And then we move on to actually making the best solution into the product. Here is the evaluation matrix that they use for picking the best design of paperclip. This is something we want to see here. Something that we've kind of done in our first projects, and we will do some more of. But you can see here that you have reliability, compact design, weight, convenience, and low cost. And you have the weighting of each of them, the 5, the 3, the 3, the 5, and the 1. Convenience and reliability are weighted at 5 because they're most important to this group. And then they take 7 designs of paperclips. We only saw 5 of them. Look, they're looking at 7 designs, and they're going to rank each one of these in each one of these categories. So the first option, the first design, got a ranking of 5 in reliability. So they take the 5 that they ranked it, and they multiply by the 5 of the weight, and they get the reliability number for this paperclip. It ends up being a 25. And you do the same thing for the next category, next property, which is the compact design. It's rated at a 1 for the for compactness, and the weight of that is a 3, so 1 times 3 is 3. And when you're done doing all these properties for each one of these options, then you add up the scores. And you're going to get a paperclip, or maybe 2 paperclips, or who knows, that rank the highest. In this case, option 7 ranked the highest with a score of 70 because it had really good scores in both reliability and convenience. And so it is obviously the one that you should look at the most. You might take a look at some others that scored high as well. For example, you have 2 that scored 51s. But you might not look at any of the ones that scored low in the 30s and the below or the 40s even. So this is a very simple but very effective way to choose the best design. We kind of did that with our bridge design, and we're going to do more of this in the future. We're actually out of time. We were waiting for some other people to show up. They didn't show up, but I'm going to we're going to show a little video really quick on how paper clips are made really quick, just so we can see this, a little bit of this process. This is actually an engineering project by a student. I don't want to read that, I just want to see it at the end. I want to see the video at the end, so I'm just going to go back to the start here and watch one of the videos. Goodness, it's in German. Doesn't anybody have one of these things for English? Apparently they don't make paper clips in the United States. Let's try this one. It's only 55 seconds long. So here we have wire on a spool, steel wires coming off the spool, going into the bending machine. So this bends the paper clip. Each one of those stations let's see if we can see it. So each one of these is designed to bend the paper clips in a different direction. And here they're actually cutting them and sending them out of the machine. Where are they coming out here? There they are. So each one of those little wheel sections that has the 3 wheels is designed to bend the paper clip as the wire runs through it. And down here they're cutting away. But it's actually a very simple process. Fairly complicated machine, but it's a simple thing. We're just bending a piece of wire and cutting it, sending them out. All right? And you can see that the complexity of that machine is going to require a fairly a fairly competent engineer to design. It's not going to be just a very simple thing. Here you can actually see a very close-up view of this bending. That's for nails and staples. But it looks very similar to this one on the top here, where you have a wire coming through the middle and you have wheels that do the bending. You know? So as this machine moves up and down, it bends the wire around the wheels. So anyway, that's what we've got for you today. Let's see. Let's take a look at our homework, because we do have homework this chapter, I believe. In chapter 5, we have problems 2 and 4, right? And remember that those are the problems that have quite a bit involved in them. You're picking a household item and list as many creative uses as possible. That should take about a page, remember. And then number 4, and that can include diagrams and everything else, should be typed up as well. And then number 4, how could you keep raindrops from blocking the view through a windshield without using windshield wipers? 5 ideas. You're not just writing them down, you're also drawing pictures, diagrams, anything that you can to explain this idea. Another page or 2 maybe. So try at least 2 pages, maybe as many as 5 pages for these 2 problems. So don't forget to get those done. And we will come back and revisit Chapter 5 on Friday. Will be our last day of Chapter 5, I believe, before we start our new project next week.
No class on Friday.
Oh, sorry, no class on Friday. I keep forgetting we have no class on Friday. We will not finish Chapter 5 on Friday. We will meet on Monday and decide whether or not we're going to finish Chapter 5. But get your homework done over the weekend for sure. We will definitely get back into doing projects now and applying some of this understanding now of the engineering process. So. I keep forgetting that I have this meeting on Friday I'm supposed to go to.